All right, today we are diving into a really powerful theory about how our minds actually work. It's a concept that pictures our thoughts as this dynamic, interconnected web. It's called connectionism.
But let me ask you a question to get started. Is your brain basically just a computer running lines of code? For a long time, that was a pretty dominant idea. But what if it's not that simple? What if thought is something messier, more intuitive, and totally different?
So, to really get a handle on connectionism, we first have to appreciate the problem it's trying to solve, which is the huge mystery of what's actually going on inside the brain's black box. Think about it for a second. When you recognize a friend's face in a crowded room, you don't go through some logical checklist, right? It just happens. It clicks. Our thinking often feels more like pattern recognition than some formal step-by-step program. And it's exactly this messiness that the traditional models have a really hard time explaining. Okay. And what's so cool about this slide is how it frames the whole debate. The classical view sees forming a belief as this clean, logical statement, almost like a line of computer code. But the connectionist view, it suggests it's more like a fuzzy pattern, kind of like a wave of activation spreading across a whole network of neurons. One is neat and tidy, the other is dynamic and spread out.
So how can we possibly model this fuzzy process? Well, this brings us right to connectionism, which completely shifts our focus from logical rules to these interconnected networks.
And here it is, the formal definition. Connectionism models are cognitive functions, things like memory, learning, and perception, not as some central processor calling the shots, but as the collective behavior of a massive network of simple interconnected units, a lot like the neurons in our own brain.
And this isn't just some vague metaphor either. Connectionism is grounded in the super rigorous mathematics of graph theory, which is the study of nodes and the connections between them. This actually allows scientists to create formal, testable models of how the mind is structured and how it works.
Now, this is such a powerful idea. It suggests that knowledge isn't stored in specific spots, like files on a computer. Instead, it's sub-symbolic. It exists in the strength and the pattern of the connections across the entire network. Think of it less like a dictionary with neat definitions, and more like that whole web of associations you have for the word summer. It just gives us a much more fluid and frankly realistic picture of how we learn.
But here's the thing, these networks aren't static. The most fascinating part is how they adapt and change. So let's explore how a connectionist network actually learns from experience. Okay, this is where things get really deep, because turning an abstract concept like learning into a precise mathematical formula, well, that's one of the biggest challenges in this entire field. How do you write an equation for getting smarter?
And scientists have developed some seriously heavy-duty mathematical tools to tackle this. They've found ways to measure how flexible a network is, because you want it to be flexible enough to learn new patterns, but not so flexible that it just memorizes every single example it ever sees. The goal is what they call probably approximately correct learning, which is a mathematically sound way for the network to make smart generalizations, instead of just memorizing things by rote.
But at its core, the process is actually this really elegant loop. The network gets some input, let's say a picture of a cat. It processes that picture through all its current connections and spits out an output. Maybe it guesses dog. Then it compares that guess to the correct answer, cat. And based on how wrong it was, it makes these tiny adjustments to the strengths of its internal connections. It does this over and over, thousands of times, getting just a little bit better with every single pass. Okay, but this isn't just some cool theory. Connectionist models are being used right now to simulate and explain real-world cognitive abilities that, not too long ago, were just incredibly mysterious.
So, we're moving from the abstract ideas to concrete applications. Researchers are literally building these virtual networks to see if they behave the way human brains do. It's a really powerful way to test theories about our own minds. And just look at the range of stuff they can explain. Everything from how we learn categories and somehow form memories in a single go, to complex language skills like how we figure out the past tense of verbs, and even visual tasks like mentally rotating an object in our heads.
Let's just pick one, that category learning example. The alcove model is amazing. It shows how we can learn what makes something a bird, not by memorizing a strict definition, but just by being shown lots of examples. Robins, penguins, eagles. The network figures out the pattern all on its own, just like a kid does.
So let's zoom out for a minute. The rise of connectionism has kicked off one of the most important intellectual debates in modern cognitive science. It really gets to the very heart of what intelligence even is.
And this is the core question. right? Is the network the whole story? Is our intelligence just something that emerges from these complex connections? Or is there another layer on top of it all?
This slide just lays out the two camps perfectly. On one side, you've got connectionism, which argues that intelligence is a bottom-up thing. It emerges from the network. On the other side, the classical view argues intelligence is top-down. It's all about manipulating symbols, like words or numbers, according to a set of rules.
So, the main critique that gets thrown at connectionism is this. Sure, the neural network might be the brain's hardware, the physical stuff, but the real thinking, the software, is a symbolic system that's running on that hardware. In this view, the network isn't the thought itself, it's just the wetware that the thought runs on.
But, the debate is evolving. The most exciting new work is actually trying to bridge this gap. Researchers are exploring how these rhythmic pulsing patterns in a network, these oscillatory networks, could actually give rise to the kind of structured, logical thinking that the symbolic systems are so good at describing. It's an attempt to get the best of both worlds.
Which leaves us with a final and kind of mind-bending question. Is your consciousness, your sense of self, every single belief and memory you have, is it all simply the unique, ever-changing pattern of activation firing across your own personal neural network? It's a profound thought, and it's one that sits right at the frontier of understanding who we are.